Good morning, Applied Physics students. So, Chapter 4, Sections 5 through 8 is kind of long. So, I'm going to do Section 5 by itself and Section 6 by itself, and then, so I'll break it into 3 videos for you because there's quite a bit of information, and so kind of at the end of each section would be in kind of natural spot to take a little break and think before proceeding. So this is just going to focus on the section 5, which is titled Free Fall, How Fast, and Falling. We're going to be start by talking about falling objects. So it may be helpful to have a calculator, especially if you're not so good at math in your head like I'm not. So you may want to have a calculator, and I would highly recommend that you take some notes. So we're going to be talking about falling objects, and obviously we want to figure out how fast these objects are falling. And I think that you are quite familiar with the fact that it is gravity that causes objects to accelerate. So remember, we've been talking about acceleration downward once the object begins falling. Your textbook talks about an apple falling from a tree, right? A paper falling off of your desk, a book falling off of your desk, okay, or a table, right? You're familiar with the fact that an object, when there's not some sort of force to support it, is going to fall. Now, in real life, okay, or out in the real world, okay, air resistance affects the acceleration. And again, acceleration means the rate at which the velocity changes. So how much faster something is moving over a period of time. Okay? However, air resistance makes things complicated. And because this is applied physics, we want to kind of simplify things a little bit. So for our purposes, we're going to ignore air resistance. To make our lives and our problems simpler and easier. Okay? If you discover you really enjoy this, and you want that more challenge, I'd encourage you to consider taking the physics class that's offered at Chip Hills High School every other year, because in that class you don't ignore air resistance, okay? But because we're in applied physics, because we want kind of simple math, we're going to kind of pretend that air resistance doesn't exist, okay? It's going to make our lives a lot easier. So we want to talk about free fall. And again, what free fall is in terms of science and physics. In free fall, an object is moving under the influence of the gravitational force only. So in free fall, the only force that's acting on the object is gravity. Okay, that's what we're saying here. So only gravity acts on the object. And again, we're going to ignore the air resistance. Okay, so when we're talking about something free falling, we're talking about an object that is only being affected by gravity. So the only thing that is going to change how it's moving is gravity. So we want to take a look at table 4.2. Let's see. So I'm going to put that on my next slide here so that we can see it. So we want to take a look at this table. And I want you to kind of just reference the table and write some notes here. Okay. So I want you to notice that our speed increases, right, each second. So what we have here is our time, right, and our time 1 second, 2 seconds, 3, 4, 5, 6, okay? And then what we have over here is our instantaneous speed, right? So this is what would be measured if we had a speedometer, okay, on an object, okay? If we pretend like it's a rock with a speedometer on it, right? And here at the top, before I drop it, it's not moving. And after 1 second, it's moving 10 meters per second. After 2, 20, 30, 40, 50, okay? So what we want to notice, our first thing that I kind of want you to not kind of write down and notice, okay, is that our speed increases each second. And how much is it increasing by? Right? Notice it's constantly increasing by the same amount, okay? So it increases each second by 10 meters per second. So that's the first thing to kind of notice. Another thing to notice about this is gravity is a form of acceleration, okay? So we have acceleration here, which is a gain in our speed, which is 10 meters per second squared. And eventually here today we're going to talk about the fact that that is the acceleration due to gravity, right? The only thing that's acting on this object as it falls is gravity. So if it's increasing, if it's accelerating by 10 meters per second squared, the only thing that can be causing that acceleration is gravity. Okay? So I want you to also kind of remember what our acceleration equation was. Our equation for acceleration was that it was our change in speed, or we could even say our change in velocity over our change in time. Which in this case, our change in speed each time is 10 meters per second. And the change in time is 1 second, which gives us that acceleration of 10 meters per second squared. Also, kind of something we notice on that table is the term elapsed time. Okay. Elapsed time is the time that has elapsed which is just kind of a fancy way of saying past. Since the beginning of any motion. So we kind of want to take a look at one thing that we kind of notice at the end of this graph here is our instantaneous speed is equal to 10 times t. The 10 comes from the fact that that is the acceleration due to gravity. So we could say that that's AT, okay? So we want to take a look at a problem. If an object at rest is dropped from the top of a cliff, how fast will it be going at the end of 1 second? Right? And again, remember, how much speed did we say on that graph? How much speed did we say the object was picking up in a second? It was picking up 10 meters per second. So to answer this question, how fast is it going to be going at the end of 1 second? Well, it started at 0 and it's fallen for 1 second. So now it's going to be going 10 meters per second because it's going to have picked up 10 meters per second of speed each second it falls. So how fast would it be going, okay, at the end of 4 seconds? Right, so each second it falls, it picks up 10. So it starts at 0. After 1 second, it's going 10 meters per second. After 2 seconds, 20. After 3 seconds, 30. And after 4 seconds, it's going to be going 40 meters per second. Because it has picked up 10 meters per second each second it's fallen. Because the acceleration is 10 meters per second squared. So let's take a look at the think question that's on page 53. Page 53 think question says, during the span of the second time interval in table 4.2, the object begins at 10 meters per second and ends at 20 meters per second. What is the average speed of the object during this 1 second interval? What is its acceleration? So I'm just going to summarize some of the information they gave us. So the object begins its initial velocity, okay, we'll just call it V1, is 10 meters per second. And it ends, so its second velocity or speed is 20 meters per second, right? And it's just a velocity when I say it's downward. As soon as I say downward, it becomes a velocity instead of just a speed. So we want to know what is its average speed of the object during this 1 second interval. So our time is 1 second, they tell us. So we're going to calculate this average just like we do an average in your math classes, right? Our average speed or velocity, we're going to add up our numbers and divide by the number we have. So our numbers are, I'm going to kind of write it as an equation first. It's going to be V1 plus my second velocity divided by 2 because there's 2 of them. So it's 10 meters per second plus 20 meters per second divided by 2, which gives me 30 meters per second divided by 2. 30 divided by 2 is 15. So the average speed during this 1 second of fall is 15 meters per second. Okay, on average, right? Not instantaneous, but on average, it's falling 15 meters per second during that 1 second interval. Now, what is its acceleration? Well, the only thing that is accelerating it is gravity. And what is gravity's acceleration? 10 meters per second squared. Now, we can also calculate that because our acceleration is our change in velocity over our change in time. Our change in velocity, so v2 minus v1 divided by our change in time. Our final velocity, or our second velocity, was 20 meters per second. I subtract 10 meters per second. My change in time was 1 second. So that gives me 10 meters per second, which is 10 meters per second squared. Okay, so we can kind of answer that 2 different ways. We can say, oh yeah, well, I know the only thing accelerating this is gravity, so it has to be 10 meters per second squared. Or I can calculate it. So, again, kind of continuing to talk here about this free fall. The acceleration of an object in free fall, which remember means only gravity is acting on it, is about 10 meters per second squared down. And we have to include down because acceleration is a vector quantity. And remember, things that are a vector quantity need both a size or magnitude and direction. So we can say that in free fall, the acceleration is due to gravity. Okay, and what that means is A is usually what we use to represent acceleration, but because the only acceleration is due to gravity, we're going to kind of substitute it with a g. Okay, so our acceleration, because it's due to gravity, we're just going to use a g to represent gravity. Now, if you take that math-based physics class at some point, you'll learn that gravity is actually 9.8 meters per second squared. But again, because in applied physics we're trying to keep our calculations simple, we're going to use 10 meters per second squared as our acceleration due to gravity. So we're always just going to make it simple because multiplying by 10 or dividing by 10 is pretty simple. So we're just going to make our gravity always 10 meters per second. The other thing to kind of know about gravity is that gravity, and therefore the acceleration due to gravity, varies depending on where you are on Earth. So the gravitational pull on Earth isn't always the same everywhere. At the bottom of a valley a really deep valley, it's actually a little bit more. At the top of a high mountain, it's actually a little bit less. But again, we're not going to worry about that in applied physics. We're just going to say acceleration is 10 meters per second squared. Now, the other thing to keep in mind is you may have a problem in your textbook where they take you to a different planet, like they say Pluto or Mars. Well then, right, the gravity on Pluto or Mars isn't 10 meters per second squared. Somewhere your book's going to have to give you that information about what the gravity is, okay? So in free fall, when an object starts at rest, okay, the instantaneous speed, okay, and we're going to say, or velocity, because again, speed and velocity can really kind of be used interchangeably, the only difference being that velocity has a direction, which we're going to represent with the little v, is equal to the acceleration, which again, because we're talking about free fall, we're going to represent with a g for gravity, times the elapsed time, which is a t. So our equation becomes v equals gt. So if we want to figure out the velocity after a certain amount of time, we can use this equation. Also in free fall, if we're going to ask to figure out the average speed, that's a little bit different. And if we're asked about the average speed, it's going to be in a straight line with constant or steady acceleration. Okay. It's calculated by finding the average of the two numbers, like you do in math class when you find the average of numbers. So you're going to add the numbers up and then divide by 2. Okay, so just like you do an average in math class. Do keep in mind that average speed and instantaneous speed are usually not the same. Okay, so average speed, instantaneous speed are different entities or different things. So I'd like to take a look at the page 54 think question. And the page 54 think question says, what would the speedometer reading on the falling rock shown in figure 4.8 be 4.5 seconds after it drops from rest? How about 8 seconds after it drops? So again, if I kind of summarize the information for my story problem, What would the speedometer reading be? That's asking about our instantaneous speed or velocity. Okay, it's a falling rock, so it's going to be moving in a straight line at constant velocity or constant acceleration. And our time is 4.5 seconds. And then we also want to know when the time is 8 seconds. So we're going to use that equation, okay, that we just saw over here, the velocity equals gt. So velocity equals gt. My g is 10 meters per second squared. That's my acceleration due to gravity. My time is 4.5 seconds. So 4.5 times 10 is 45. And my units, if I take a look at that, I have meters per second squared times a second. So that crosses out one of those seconds. So my units are going to be meters per second, which makes sense. I would expect my velocity to be 45 meters per second. Again, it's falling, so we could add that direction of down to make it a velocity. So then we do the same thing for the second one. Our equation is still our velocity equals our acceleration due to gravity times our time. Our acceleration due to gravity that we're going to use is 10 meters per second squared. Our time this time is 8 seconds. 10 times 8 is 80. And our units are going to be meters per second. And again, if I want to make it a velocity, I can say it's going to be down. So, I want to look at that table again, table 4.2. But I want to add something to this. We have the instantaneous speed. I want to add our average speed. So I'd encourage you in your notes to kind of copy this, okay? So remember how we're calculating our average. We're taking our final velocity or our second velocity, adding it to our first velocity, and then dividing them by 2. So when I go from 0 to 1, I add 0 plus 10, which is 10, divide that by 2, which is 5. So my average speed during my first second, okay, is 5 meters per second. Now I do the same thing for 10 to 20, right? So 10 plus 20 is 30, divided by 2 is 15 meters per second. So this is in the first second, this is in the second second. Here's my third second. 20 plus 30 is 50. Divided by 2 is 25. Here's my fourth second. I'm starting at 30, I end at 40, so that's 30 plus 40 is 70. Divided by 2 is 35 meters per second. And during my fifth second, 40 plus 50 is 90, divided by 2 is 45 meters per second. Okay, so this is our average speed during these time intervals. During our first second, our average speed is 5 meters per second. During the second second it's falling, average speed is 15 meters per second. During our third second of fall, our average speed is 25 meters per second. During our fourth second of fall, our average speed is 35 meters per second. During our fifth second of fall, our average speed is 45 meters per second. Okay, eventually that's going to become important for us to sort of use to figure out where our object is. So next we want to continue talking about objects that are falling, but now we're going to talk about rising objects, which just means that we're going to talk about objects that instead of being dropped straight down, these are objects that are first going to be thrown straight up in the air and then start to fall. Okay? So with rising objects, now we are going to consider objects thrown straight upward. And again, you should know from experience that these objects, first they travel upward, then that object momentarily stops at the top of its path, and then it comes back down. You've thrown an object straight up in the air before. Now, kind of thinking a little bit more about that, as that object travels upward, what's happening to its speed? Right? You know that the speed of the object decreases. What happens at that very tippy top? What happens to the speed of the object there? Hopefully you said the speed of the object is 0 meters per second. Right? It momentarily stops. And then as that object travels downward, what happens to its speed? Right? The speed of our object increases. Again, it's only one force acting on this object because, again, we're ignoring air resistance. So the only force acting on the object is gravity. And what did we say about the acceleration due to gravity? Right? Gravity's acceleration is equal to 10 meters per second squared downward. Therefore, gravity slows the object down 10 meters per second each second the object rises. And, okay, therefore, the object's speed increases 10 meters per second each second the object falls. So we want to take a look at figure 4.9. We want to take a look at, okay, so we're going to kind of look at the instantaneous velocity, our average velocity, and our acceleration. So I'm going to put that picture here. But I'm going to kind of repeat it and kind of show you how I don't necessarily need to look at this picture. Okay, so I've got my little person here. And I'm throwing a ball. So here's my ball, right? And I know that I'm going to throw it upward. Okay, so we're going to say it's right there at the start. Now, I'm just going to kind of copy where they put the ball at. But then we're going to kind of talk about how they get those speeds. Okay, so let's talk about what's acting on this. First off, right, the only force that we're going to talk about is gravity. And remember, a gravity is g, which is an acceleration, and it's 10 meters per second squared, and it's downward. So it's going to be important we kind of keep that in mind as we look at this. So first thing that I'm going to kind of do in purple here is I want to look at my instantaneous velocity or speed. Now, we know what it is here, right? It's 0 meters per second, or sorry, in our picture, right? We're starting, because we're throwing it. So we're starting with a 30 meter per second throw. And it's a velocity, right? So it's going upward. Now, each picture, okay, each time here is 1 second. So we can also kind of put here that our kind of picture shows the ball at 1 second intervals. So what we see next here is where the ball is 1 second later. So this time that's passed, okay, is 1 second. So the acceleration due to gravity, we know it's going to have slowed it down, okay? And here it's now going to be moving 20 meters per second. Because it's 1 second and it slowed it down by 10, it's still acting upward. Our next second, we're going to lose 10 more meters per second of speed. So we're at 10 meters per second, and it's still acting upward. Now, what did we say happens at the very, very top, right? We have no speed. It stops. So this is 0 meters per second. Now it starts to fall, correct? And gravity is going to accelerate it. It's going to make it pick up speed. How much speed? 10 meters per second every second it falls. So 10 meters per second. But this time my velocity is acting downward. Here I'm going to pick up 10 more meters per second. So it's 20 meters per second. Also acting downward. Here I'm 30 meters per second, acting downward. And down here at the bottom, I have 40 meters per second, acting downward. So our total time interval, right, that we've shown here is 1 second, 2, 3, 4, 5, 6, 7. So let's go ahead and kind of put little times in here. Okay, right, so this is t equals 0 seconds. This is t equals 1 second. This is t equals 2 seconds. Here at the top is t equals, I'll have to put it over here, sorry, 3 seconds. 1 more second, so this is t equals 4 seconds. T equals 5 seconds. T equals 6 seconds. And t equals 7 seconds. So there's our times. Okay. So remember, I said I wanted to look at our instantaneous velocity, which we have, our average velocity and our acceleration. Let's look at acceleration next, right? What's the only thing that's acting on this object, the only force? Gravity, right? So the acceleration here is 10 meters per second squared, and it's down. Acceleration everywhere here is 10 meters per second squared, down. Acceleration equals 10 meters per second squared, downward, right? That's why as the ball is rising in the air, it's losing speed, and as it's falling in the air, it's picking up speed. So notice our acceleration here has never changed. Our acceleration, due to gravity, is constant. It's unchanging. It's always 10 meters per second squared downward. All right, the last thing we wanted to look at was our average velocity. So we're going to use some pink. Okay? So our average velocity from here to here, I have 30 meters per second plus 20, which is 50, divided by 2, which is 25 meters per second. Okay, so this is my average speed or velocity that I'm getting by adding them up and dividing by 2. So here, right, 10 plus 20 is 30, divided by 2 is 15 meters per second. Right here, 10 plus 0 is 10, divided by 2 is 5 meters per second. Now notice something, right? One little quinky dink about this. Notice at my same position, my speed is the same. They're acting in different directions, but the number itself is the same. So my acceleration, okay, due to gravity, or my average velocity here is still going to be 5 meters per second. Okay, in this interval here, it's going to still be 15 meters per second. Here, it's going to be the 25 meters per second. And from here to here, it's going to be 30 plus 40, which is 70, divided by 2. It's 35 meters per second. Okay, so that's where kind of all of this comes from. So that brings us to the end of this first section. I hope this has helped. If you had some questions, have a great day.